My name is Stuart Swan. I'm a platform architect at Siemens EDA in the Catapult high-level synthesis group. And I'm going to be talking about NVIDIA's use of Catapult HLS for building machine learning inference accelerators. And it's kind of funny that the previous talk was about Catapult. Also, this is a different Catapult. It is specifically doing high-level synthesis, which is basically taking a C++ specification of a hardware accelerator and automatically generating the gates and the layout and providing a flow all the way to the hardware implementation. And this presentation actually uses a combination of slides from both NVIDIA and Siemens EDA. It'll be pretty easy to tell which are which because the NVIDIA slides are all green and the Siemens slides are all blue. So real quickly, what is the motivation here? And this is a slide from NVIDIA. And basically, they're recognizing that what's limiting them from putting features in and developing more complex chips is the time and effort in doing RTL design and verification. And in their own analysis, it's 70% of the IC design effort at NVIDIA. And it's very easy to say, well, if it's 70% of the effort, it's roughly also 70% of the cost of developing these chips. And if you're familiar with the cost of developing these state-of-the-art chips, it's high. It's, and sometimes well over $100 million to develop these very advanced SOCs. And so their goal is to have a dramatically lower cost of designing and verifying these types of chips. And so to achieve that goal, they've developed a new methodology around designing hardware and verifying hardware at a higher level of abstraction. They're using C++ and they're using high-level synthesis. And basically the idea behind high-level synthesis is that you're developing at a significantly more abstract level than RTL design, which is the prevalent design methodology out in the semiconductor industry today, where you're basically writing Verilog RTL, where you're tying every operation to a specific clock cycle over a span of time. High-level synthesis, you're not tying every single operation to a specific clock cycle, and you're leaving it the tool to figure out the optimal implementation. They also want to have this, what they call agile design here. Instead of having teams of hundreds of engineers, you have small teams of around 10 engineers that are engaged in all aspects of the design and verification effort, all the way down to the layout and prototyping, and having very fast spins where you're modifying the C++ code and going all the way to a fully placed layout in 24 hours. And this is sort of analogous to the agile development methodology that you see in the software development world. The last thing they do, which I'm not going to talk about very much in this talk, is the use of multi-chip modules and network-on-chip technologies to basically scale the size of the system. So how does high-level synthesis and what this library that they developed called Matchlib help raise the hardware design abstraction level? Well, the first thing is that the high-level synthesis basically automates a lot of the tedious details that RTL designers would typically have to do. So it optimizes the scheduling across clock cycles based on the selected silicon target technology. It automatically constructs the hardware pipeline according to the user's specification. So much of these types of designs process huge amounts of data and have to shuffle data around the chip just in time to do the required operations. And basically, the tool can automatically construct these pipelines rather than having hardware designers have to deal with all the details. The tool can do automatic hardware resource sharing and scheduling of memory accesses. And then very importantly is that because it has a very fast path to RTL implementation, you can very quickly evaluate alternative architectures. And this is really a key benefit because with these new machine learning algorithms, new machine learning techniques, the designers don't always know the optimal architecture. So you need to be able to explore different architectures and find the optimal one. The other thing is that Matchlib and System C provide a very accurate simulation environment very early in the design process. So basically, there's this notion of throughput accurate modeling that enables you to see what the final performance characteristics of the system will be very early in the design process. And the simulation is very fast. It's about 30 to 300 times faster than RTL, and it's very accurate. It's within 3% accuracy of the RTL simulation. And it's about 10 times fewer lines of code than the RTL. And there's many different building block IPs that are available that are sort of pre-built to provide good foundation models that will synthesize to silicon with good quality results. And lastly, you can apply RTL verification techniques at this level. So you can do constrained random testing, you can use system Verilog EVM, you could do coverage and so forth. So just real quickly, this is a kind of give you an idea of what the simulation looks like in what we call the pre-HLS simulation. You see waveforms that look very much like an RTL simulation. When you synthesize that design through Catapult high-level synthesis and you're doing the same simulation in Verilog RTL simulation, the simulation will look very similar. You basically see the same waveforms. What's different is that because the high-level synthesis tool is going to pipeline the design, the latency will get a little bit longer. But in terms of the signal level activity and the transactions flowing through the system, it's basically identical. So this is an example of a machine learning accelerator that NVIDIA research developed a few years ago using basically this methodology for the entire chip. It's basically a multi-chip module that contains a 6x6 array of these chips. And then each chip contains a 4x4 array of processing elements that do the heavy-duty lifting for the machine learning computations. And then they have a global buffer for weight and input storage. And they also have a RISC-V processor on board to basically coordinate all the activities between all the elements in the system. And there's an AXI bus, and then there's off-chip, network-on-chip interfaces, and so forth. We can zoom in a little closer on the processor element here and see that basically the core functionality within each of the PE or processing elements is a vector multiply accumulate hardware block. It's a pipelined multiply accumulate block that is designed for very high performance, where you basically can take in a new set of samples on every clock edge and do all the multiply accumulates and stream them in and stream them out without any gaps. And basically, this entire processing element is fully designed in C++ and fully implemented by Catapult high-level synthesis in 100% pipeline fashion to achieve optimal utilization in the hardware. This is very quickly an example or a summary of the actual working chip. This is a photograph of the actual silicon die. You can see the small RISC-V processor here. You can see the 4x4 PE array. You can see the different blocks for interfacing with the network on chip on the periphery of the block. And then there's basically a 6x6 array of these chips that are put onto a package that communicate via network on package network. And this design is actually a few years old, but it's openly published. There's research papers available that are noted here on the slides. But the key thing I want to point out is that the peak performance, which is measured of trillions of operations per second, at the time that this was released, is really industry-leading, world-leading at that time. And the energy efficiency, which is another very important metric, is also world-leading at that point in time. And these are very commonly used machine learning networks that they are able to map onto this system and show actually running with real results. I will note that NVIDIA is still using this methodology, and I'll provide some pointers to some more recent results with this methodology. But just to summarize here, the idea here is that Matchlib and Catapult HLS enable a fully modern design and verification flow where the designer is able to focus primarily on the chip architecture and functionality and throughput analysis and verification. Doesn't need to worry about all the details that he would normally need to worry about if we were doing this type of design at the RTL level. And then the high-level synthesis tool basically automatically adds pipelining and optimizes the microarchitecture and provides a fully automated path to placed gates so that you can do these rapid spins and explore multiple architectures and also basically eliminate bugs in the system very early. And the idea here is that the focus of the verification effort then moves up to the C++ and System C level, enabling much greater efficiency. And this is very important because much of the cost of developing these types of chips is RTL verification. You want to reduce that cost and move the verification effort higher in abstraction. So real quickly here, I'll give some brief links to get some more information. You can Google for Catapult high-level synthesis. There's a very good YouTube video made by the director of research at NVIDIA that talks in more detail about Matchlib and Catapult HLS and does actually talk about this particular design. You can also look at the various research papers that NVIDIA's published on this methodology. And then Bill Daly at Hot Chips just recently in 2023 mentioned some of the most recent research results that use this methodology. You can just Google here. There's a link in his talk on the NVIDIA website to some of the papers, the 2023 research papers that are related to this methodology. And lastly, there's a set of examples that are posted on the Accelera website that provide a very broad set of examples that show how these models are written. They actually run. It's a fully contained kit. You can download it and run it on any Linux system and see for yourself and get a feel for how this works. Okay, thank you.